Welcome to our lecture series on protection technology. These 3 Siemens Power Academy lectures are designed for those who want to expand their knowledge and understanding of relay protection for distribution and transmission grids. Today we will focus on the physical basics of sensitive ground faults, mainly for professionals from distribution and transmission grids. We will record the webinar and make the recording and the slides available to all participants. Please type your questions in the Q&A field. We will answer these during the dedicated Q&A session after this series. And now let me hand over to our expert Prof Lemmer. The stage is yours.
Hello, today's topic is sensitive earth fault detection. That means I will describe how we can detect earth faults in systems where the start point is not solidly grounded, either floating or grounded via a reactance. And you will see detection of earth faults in such systems is not an easy task. So let's start a little bit with the physical basics to understand what's going to happen in case of an earth fault, and after that I will describe the different functions we have available for that. Let's start with a look at the different methods to treat the start point. What we know from transmission systems is solid earthing. Sometimes it's also called effective earthing. That means the start point is directly connected to ground. The opposite thing would be isolated neutral. That means the start point is open, not connected to anything. Sometimes that's also called floating neutral. And then there are a lot of things in between. One class is, unfortunately it has different names, is earth fault compensation or arc suppression, or you call it grounding with Peterson coil or resonant earthing. That's a widely applied thing. And there are a few other methods. You can also put a resistance in between start point and ground, a low resistance or a higher value. It also influences behavior. And you can also do some short time earthing. That means during an earth fault, you change the start point treatment. And we will at the end have a short look at that. Let's start first of all with systems where the neutral is isolated, and it's important to understand what's happening in such a system if we have a ground fault. This shows a simplified schematic of such a system. You see on the left side the transformer, the 3 windings of a transformer with a start point. The start point is not connected to the ground. Then you have the 3 phases. And now to consider these cases, we have to take into account the line capacities. Remember, when we discussed about short circuits, we could in most cases neglect the line capacities. Here this is not possible. That means we have to take them into account. And if such a system is in normal operation, we have the load current flowing, and the line capacities are charged and discharged depending on the voltage difference between the conductor and ground. It's changing with the fundamental frequency. If we now have an earth fault, here indicated with the red arrow, at that particular moment where the earth fault starts, in this case in phase L3, then the line capacity of phase L3 is discharged. Now remember what happens if you have a capacitor and discharge it, you get a high current peak. In this case, it's not a concentrated element, it's a distributed element. That means the capacitor is distributed along the line or the cable, and there is some inductance involved. That means we do not get a current peak, we get somehow an oscillation with the capacitance and the reactance of the line, and that oscillation is called the discharge oscillation. That's indicated here in green. that has a pretty high frequency. The frequency depends on the type of cable, or is it cable or overhead line, and on the size of the system. After this discharge, oscillation is gone, or after it has damped out, we have a charging oscillation. And that means, because now one phase is connected to ground, the potential of the other phases rises, and we have to charge the two other capacitors. And this charging runs through the transformer. That means a higher inductance is involved in that. It's again an oscillation, here in purple color, and this oscillation has a lower frequency. That means if the fault happens, we have the discharge, the green oscillation, then the purple oscillation, and after that we have this situation with a permanent earth fault, and it's important to have a certain understanding what's happening there. In the first glance, it's a little bit strange that although the star point is not grounded, we have a current flow there. The current flow, or the current value, is not very high. We will see that. To understand that, please imagine that these transformer windings, you can represent them as voltage sources. That means we have 3 voltage sources on the left side of the picture. And even although we have an earth fault here, the voltages will remain there. There are no short circuits, currents flowing, so the voltages will remain there. That means phase L3 is connected to ground. And if you now look at phase L2, you have a series connection of the voltage source transformer L3 plus voltage source transformer L2. These two voltages are connected in series, and they feed a current through the capacitor representing phase L2. That is one of the blue currents. And we have series connection of voltage source L3 plus L1 driving a current through the capacitor representing phase L1. And that means we have a permanent current flow at the earth fault. And this current flow, you can imagine that if you look at this diagram, is determined by the size of these capacitors. We will come to that later on. Before we do that, I would like to have a short look at the voltages. On the left side, you see normal operation. Although the star point is not connected to ground, in normal operation, it basically has ground potential as long as these capacitors are identical. That means, for instance, if you are in a cable system, the capacitors are really identical, there's no big asymmetry in it, then the potential of the star point is nearly ground potential. If you are in an overhead line system, there can be a slight asymmetry so that you get a little bit a deviation. That means we have this triangle there, and this point in the middle is ground potential. And you see all phases have a phase to ground voltage, which is rated voltage divided by square root of 3. And between the phases you have the rated voltage. If you now have a ground fault, this triangle remains there. That means the relation between the phases remains there, but one corner of the triangle is connected to ground. So you get this triangle on the right side. That means the phase to ground voltage L1 is 0. And what you also see is that the voltage in the two other phases rise by the factor of square root of 3. That means in a 20 kV system, suddenly the phase to ground voltage of the two other phases is no longer rated voltage divided by square root of 3. It is rated voltage. Phase to ground voltage in a 20 kV system would then be 20 kV. That were the voltages. Now let's again come back to the current. let's have a look at the current. How can we calculate the current? So you see here on the left side again our system, and here we could do a simplified hand calculation, but the normal way to calculate such a system is using symmetrical components. Why do we do that? In a three-phase system, we have the situation that every current influences every other current. That means if you make a mathematical representation of such a system, you get a matrix where all elements are filled. And hand calculations with that are normally not that easy. And for that reason, it's a common way of practice to use the so-called symmetrical components. That means you do a mathematical transformation from this real world into the world of symmetrical components you see on the right side. And there you get an equivalent circuit for that, which can be simply calculated. And once you have done the calculation there, you get a result and you convert that back into the real world. And that is done here for this example, earth fault in our system. We transform that into the world of symmetrical components. You see we get there a positive sequence system, which consists of a transformer. Replica for the transformer is just a voltage source with a transformer impedance. We have a negative sequence system. Symmetrical components are always these three systems. Negative sequence system in this case consists only of an impedance, transformer reactance. And in the zero sequence system, we have mainly the capacity of the line. And all these three systems are series connected. And then we can calculate the current in this circuit. Because we have one driving voltage, we have some impedances, and you see the equation down there. And we can calculate this current I naught. It's the zero sequence current. And once we have done that, we can transform the result back into real world. That transformation in this case is pretty easy. We just have to multiply it by 3. And that is why you find on the bottom line the fault current is 3 times zero sequence current. Now let's look at the zero sequence current. It's driving voltage divided by impedances. And if we look at the value of these impedances, we can more or less neglect the reactances we see there. That means the bigger impedance, 3 impedances are zero connected, and one of the 3 impedances is really the biggest one, that is the impedance formed by the line capacity. So that is really, the line capacity is really the influencing thing. And if you solve that, you see as the result that the fault current is square root of 3 multiplied by rated voltage multiplied by omega, which is 2 pi multiplied by frequency multiplied by the line capacity. That is the current, the earth fault current we have under permanent earth fault conditions. We can summarize that. In such a system with isolated neutral, the current we have under earth fault condition can be calculated from voltage and line frequency. That means the earth fault current is defined by, first of all, the type of lines. Do we have overhead lines or cable? Because cable have much higher capacity than lines. So in cable systems, the earth fault current is much higher. Then you see in the equation the voltage. That means the higher the voltage level is, the higher the earth fault current is. And you must also have in mind the capacity increases with the size of the system. If we increase the system length, we increase the capacity, and that means we also increase the earth fault current. The strange thing here is this earth fault current, and we will see values later on, are much lower than the normal short circuit currents. In a normal short circuit, we have currents in the range of kiloamps. We have to disconnect them as fast as possible. In this case, the currents are in a range maybe 10, 20, 30 amps. It's not zero, but relatively low currents. That means you can continue operation for some time. But the really interesting thing is, earth faults may extinguish without doing anything if the current is low enough. And I will come to that point on the next slide. What we also should keep in mind, in case of an earth fault, we have a voltage rise in the two other phases by the factor of square root of 3. And that also means if you have this earth fault condition, earth fault current flowing, the voltage in the two other phases rises. And that, of course, also means if you have any weak points in the system somewhere, you may get a flash over in another point, and then you run a bit into trouble. But first of all, let's look at this self-extinguishing thing, because that is one of the big advantages of this treatment of the star points. Imagine you have a fault, an arc fault on an overhead line. Started maybe by a lightning arc from a thunderstorm. Then you have an arc between the conductor and the tower. And at the moment there's nothing damaged. There's just an arc. The arc produces heat. The heat keeps the air ionized, so this thing maintains itself. But you need a certain current to keep the temperature. That means if you make the current lower, you get less energy there. And if you bring the current below a certain value, then you don't have enough energy to keep the air hot. Then the whole thing stops. The air cools down a bit, current stops flows, and then it disappears. That means you have cleared the fault without doing anything. And that brings us, of course, to the question, what is this current limit? What is the value for this current limit? And it's not that easy to calculate it. I've here a few values that are not exact values, but just to give an estimation about the range of these self-extinguishing limit. In a 20 kV system, this limit is for a system with isolated neutral, what we are discussing in the moment, around 35 amps. That means if the capacitive current in case of an earth fault is below 35 amps, then an arc on an overhead line will extinguish without doing anything. And that is an advantage. You don't have to trip anything. The fault just disappears. If you have earth fault compensation, what we will discuss in the next part, this limit is a bit higher at 60 amps. If you go into 110 kV systems, you typically have earth fault compensation. This limit is around 130 amps, but it depends on a few other conditions. That was the self-extinguishing limit. So it's important, if you want to remain under this limit, it is of course important to know, what is now the current, how much current do we get? And this table gives you some indication about the current. On the upper part in the table you see for overhead lines, what currents do we get per kilometer? Let's take an example, 20 kV network. You get 60 milliamps per kilometer. That means if you have a system with 100 kilometer, you would have a capacitive earth fault current of 6 amps. That means you would be under this self-extinguishing limit. It would work. If you have a cable system, it looks pretty much different. In the lower part of the table you see, for instance, for a 20 kV system, values between 2 and 5 amp per kilometer. That would mean already with a system with a total cable length of 10 kilometer, you are already above the self-extinguishing limit. And you must also keep in mind this story, self-extinguishing faults will only work for overhead lines. In a cable, the fault mechanism is a bit a different thing. In a cable, you have typically a fault if you have some insulation problems or if you have mechanical destroyment of cable, then this self-extinguishing thing will not help. That is an advantage which mainly can be used in overhead lines. That was a look at systems with isolated neutral. Now let's look into systems with earth fault compensation. What is the idea there? And to understand what the idea behind earth fault compensation is, we can again look into this symmetrical component representation. Look in this picture at the right side, you see this symmetrical component equivalent circuit we already discussed just a few slides ago. But you see one difference here. We put in a reactance in the zero sequence system in parallel to the capacitor. The idea behind that is we saw if we make the system bigger, the capacitor grows. That means the impedance of the capacitor reduces. And then somebody had the nice idea, if I put an inductance in parallel to a capacitor, and I tune the inductance in the right way, I can make the resulting impedance of that nearly infinite. And that is the idea there, to put this inductance in parallel to the capacitance in this zero sequence representation. Now the interesting question is, of course, that is the zero sequence world. Where can this inductance be in the real world so that it shows up at that point in the transformed world? And the result is we can put it into the star point. And that is shown in the real world diagram on the left side. There you see this coil, big inductance, connects the star point to ground. And if we transform that system into symmetrical components on the right side, we get this parallel connection of inductance and capacity. And if we tune the inductance in the same way so that it has the same impedance as the capacity but different sign, then the resulting impedance of this part of our circuit is nearly infinite, and that brings the zero sequence current down, and that brings the fault current down. And that allows us to have bigger systems, and the fault current is still below the self-extinguishing limit. If we look at the voltages, it's the same story. That means the behavior in terms of voltages is the same as in systems with isolated star point. That means we don't have to discuss that again. So let's summarize again this star point treatment with earth fault compensation. We have an earth fault current which is theoretically zero. Practically, of course, it's not always zero. Practically, it depends on the tuning. As I said, this reactance must be adapted to the capacity. That means it's a tunable coil, and you must tune the coil so that it compensates the capacity. If you make an exact tuning, you have a resonance circuit, and you may have a feeling having a resonance circuit causes some resonance effect is not so nice. So it's common practice to make a little bit a detuning. That means not to tune this coil exactly that it fits to the capacities, but make a little bit a detuning of a few percent. And that also increases the current a little bit. Then, of course, the coil is not an ideal inductance. It has some resistive components. That also increases the current a bit. And then there is another aspect we have to discuss, that is the aspect of harmonics. This compensation, that means that the coil and the capacitor compensate each other, that works for the fundamental. That does not work for higher harmonics. That means with this coil we can significantly reduce the current in terms of fundamental, but if we have harmonics there, they are not really influenced by that. That means we have a current flow generated by harmonics. What is also indicated in this picture is you can, just to get a bit an understanding what's happening there, you have an overlay of the previous thing in an isolated system where you have the blue capacitive current we discussed. And with the coil, we get additionally this green current. That means the coil drives a current, or the phase L3 voltage drives a current through the earth fault and the coil. That is the green current in this case. And these two currents are of opposite phase. That means they compensate each other so that the current at the fault point is nearly zero. So that is a different way to make up your mind how this situation works. Again here, the big advantage is we have self-extinguishing faults. As long as we are an overhead system, we may continue operation under permanent earth faults, and we also have this voltage rise. And in practical applications, you can say in overhead lines we can reduce the earth fault current down to something like 5 to 8% of the capacitive current. And that means, of course, a lot. That means you can make the systems much higher, much bigger, and you still are below the self-extinguishing limit. So that was system with isolated neutral, systems with earth fault compensation. What you also sometimes find is, especially in medium voltage systems, is earthing via a resistor. That is shown here. Then we are back in the world where the star point is effectively grounded. What can you do with such a resistor? You can now make the same representation with symmetrical components. What you find then is, and that is easy to understand, that this resistor influences the earth fault current. That means the bigger this resistor is, the lower the earth fault current is. But normally you dimension the resistor in this case in a way that the normal short circuit functions we have will detect such a fault. In the compensated systems or in systems with isolated neutral, the earth fault currents are pretty low. The normal short circuit functions will not react on it. Overcurrent protection will not react, distance protection will not react, differential protection not. But here we are back in the world where earth faults are short circuits. They can be detected with the normal short circuit functions. Just to give you an idea about the value of such a resistor, in my early Siemens times, I did some projects in this area. So for instance, if you go into a 20 kV cable system and you put in a resistor around 6 ohms, you end up with a fault current of 2 kiloamps. That means with the 6 ohm resistor, you can limit the phase to ground fault currents to 2 kiloamps. And that is a good thing because phase to ground currents are the majority of faults. And in these cases, you limit the current, you produce less damage, you have less interference with some communication systems, and so on. But you must always have in mind the other fault types, like phase-to-phase faults or three-phase faults, remain the same. And that also applies for systems with isolated neutral or earth fault compensation. The discussion only referred to phase-to-ground faults. In phase-to-phase faults or three-phase faults, you still have normal short-circuit conditions. This resistance, of course, is not a tiny little thing. Imagine if you have 6 ohms, if you have 2 kiloamp flowing through 6 ohms, the power you have then in this resistor is resistor multiplied by I square. If I is 2000 amps, I square is 4 million, multiplied by 6, you are above 20 megawatt of power in that resistor, but of course only for a short time, because then the fault is tripped, and then, but that means the resistor is not really a small thing, it's a bigger thing. That's a summarize for these earth faults in system with an impedance. You also have a voltage rise in the other phases, in the fault-free phases, is a bit reduced in comparison to the earth fault compensation, but it's also there. You can influence the current by dimensioning this resistor, and in this case you cannot continue operation with an earth fault. You must do selective clearing. So let's now compare these different schemes. So we have on one hand isolated neutral on earth fault compensation. On the other hand, we have low impedance earthing or even solidly earthed. What are advantages and disadvantages of these concepts? The big advantage of isolated or earth fault compensation is that many faults are self-extinguishing. And that is really a big advantage, because for these faults you don't have to do anything, you don't get any interruptions. The only limitation is the fault current must be below the self-extinguishing limit, and it only applies to overhead lines. In cables, it doesn't really work because you don't have these arc faults in cables. But that's really the big advantage, and that means also that the application of these things is not limited to overhead systems with overhead lines, but it shows the best advantages there. The other advantage is that tripping may not be necessary. That means you can continue operation with an earth fault, but of course not for days, and it also depends on legal requirements. So let's assume we have maybe 30 amps current flowing in a compensated system, 20 to 30 amps. Compared to short circuit, it's a low current. But on the other hand, if you have 20 amps somewhere in a cable, you can imagine it will produce some heat in the cable and it will destroy the cable at the location. That means after some time, something will happen down there. So continuous operation for infinite time is not possible. It's not necessary to trip the fault in a milliseconds time, but operation for longer time also has some limitations. And as I mentioned, it depends on the legal requirements. That means if you compare the concepts you see in different countries, some countries allow that, other countries require tripping. And to the end, that is a risk evaluation. That means the question is, how big is the risk that, for instance, people are injured in case you have a permanent earth fault somewhere? As long as your earth fault is somewhere in ground or on top of a tower, it's not a big problem if you have 30 amps flowing there. But imagine the following case. You have a broken conductor of an overhead line and the wire falls to ground. Then you have an earth fault. So it's sparkling a little bit, and then you have some hikers coming around saying, oh, nice wire lying there, nice sparkling there. They touch it and they are dead. That means you have a certain risk. You may say, why do they touch it? Are they stupid? But of course the risk is there. and then you have to do this risk evaluation. That means, do you accept this risk? Say the chance that exactly this happens is so low that we can ignore that. And other countries say, no, I want to protect people even against this low risk, and I require that these type of faults have to be tripped. If you have low impedance or solid earth systems, clear situation, every fault must be tripped. That means if you have a fault, the line has to be taken out of service. That can cause some interruption in the supply. The disadvantage on the left side is, and that will be the second part of this video, is the fault localization. If you have a solidly earth system, you find the fault with this concept, selectivity concept, with overcurrent or distance or with the differential protection. It's pretty easy, it goes automatically. In a system with earth fault compensation, we will see fault localization is not that easy, because these normal concepts you anyhow have for short circuits don't work. That means low impedance, it's easy. For earth fault compensation systems, it is difficult. And the other thing which can happen, remember, if you have an earth fault, if you continue operation, the voltage in the other phases rise. And if you have somewhere in the system, and that refers to the whole system, that means in your whole system, everything what is galvanically coupled has a voltage rise in the other phases. And if there somewhere in the system is a weak point in the insulation, you may get another fault at another location. And then you have a difficult situation. You have one earth fault here, and you have another earth fault in another phase at another location. And that is then now a short circuit. Because if two phases are affected, you have then higher currents flowing. And this type of fault is called cross-country fault. And the detection of cross-country faults is sometimes a bit a challenge for the protection engineers. The chance that that happens in systems with solid earthing or low impedance earthing is very low. You may have a voltage increase in the healthy phase if you have resistive grounding, low impedance grounding. But as you trip the fault anyhow after a short delay time, the chance that that evolves into a cross-country fault is much lower. So you see, both concepts have some advantages and some disadvantages, and that is the reason why we have really, in different countries, in different systems, different concepts in use. And some countries are even sometimes moving, or some utilities are sometimes moving from one concept to the other because they see advantages there. For instance, if you convert a system from a pure overhead line system more into cable system, then you lose some advantages of earth fault compensation. So it may make sense to think about the star point treatment.
Dear audience, if you're interested in more detailed information and practical training, please visit our training platform at Siemens Power Academy. I am confident you will find the right resources and training there. A link to the recording and the slides will be sent to all participants. Thank you for your active participation. I look forward to meeting you soon. Stay safe and take care. Goodbye.